Hi guys, welcome to the second part of the periodicity topic, which is ionisation energy. So far we've looked at covalent radius. The next part still uses the stuff we've been talking about in the previous lesson. So if you haven't watched that video yet, or if you're still not sure about nuclear charge or electron shells and how they affect different things in the periodic table, then go back and have a wee look at that. So hopefully by the end of this video you should be a bit happier about that stuff as well, because it's always the same stuff that we're talking about whenever we're talking about these trends that are happening in the periodic table. So this one here, we're interested in page 11 in the data book. We're not really going to be looking at it in much detail in this video, but later on whenever you're practicing questions and things on ionisation energy, we'll have a wee look and we'll get familiar with that particular page, because it will be one that you definitely need to use in the exam. So, what we need to know is what ionisation energy actually is. So the actual definition of that is a question that could come up, so that's something to remember. And then going a bit further than that is the actual deeper understanding behind it and how the element's position in the periodic table will actually affect ionisation energy. So similar to the covalent radius stuff. So there's a couple of wee things extra in this as well. So talking about writing ionisation energy equations, which we'll hopefully have a wee look at in this video, and I'll show you a kind of easy way to remember how to do that as well whenever we get to the point where we're looking at the data book. So it's basically just all about explaining ionisation energy, what it is, and how that varies depending on what element you're looking at and why that is. Okay. So, talking about what ionisation energy actually is first, so that wee bit in italics is your definition, so I would maybe even take a wee second to pause this video and write that down, okay, because that is, like I said, quite frequently asked in the exam. So basically all ionisation energy is the amount of energy that's required to remove 1 mole of electrons from 1 mole of atoms. But you'll notice that it says in the gaseous state. So basically that means that that element has to be a gas. Okay, so it could be a metal, like a solid metal that we're looking at, but that has to be in gaseous form, right? So that is what the energies that we're talking about is. Okay, so removing electrons from gaseous atoms. So down at the bottom, we're going to have a look at what that actually is, right? So it's fine knowing the definition, so hopefully this wee diagram down here will make it a wee bit easier for you to visualise. So what we've got is just a random element, M, right? So M isn't actually an element at all, it's just a made up one. So it's just kind of generally speaking so that you can see what we're going to be talking about. So in the middle, obviously, we've got our positive nucleus and we've got our electron shell round the outside. So we've got 2 wee electrons in there. So ionisation energy is where we're actually putting energy in and we're losing that wee electron. So it's normally the outermost electron, so the one that's furthest away from the nucleus, the one that's kind of least tightly held by the nucleus, that is lost first. Okay, so what we've kind of spoke about is the ionisation energy equations. So if we start off with our element in gaseous form here, what actually happens is that it becomes positively charged, so you've lost 1 electron, so it becomes +1, and we've got our wee electron there as well. So you need to be able to write equations like that for different elements. So again, we'll get practice at that as we go on. So the amount of energy required to actually do that and turn that into an ion is in the data book, right? For every single element, there will be a particular value for that, which we'll look at in a bit more detail in a minute. So then we've also got, if we do that again, we end up with the ion, which we just achieved there just now from applying that amount of energy. If we apply more energy again, we can actually make that a 2+ ion. by losing another electron. So what we call that is the second ionisation energy. So again, that'll be a different value. There'll be different amounts of energy required to be able to remove that second mole of electrons. Okay. So we can go on and do that again. We can do it for a third time to make a 3+ ion, and then for a fourth time to make a 4+ ion, and so on. Okay, so that's basically all ionisation energy is whenever we're talking about it. So the units of ionisation energy are kilojoules per mole. So we've not really looked too much at energy and enthalpy and stuff like that. We're going to do that in another topic. But just to have a wee think about it just now, so you could actually be asked if ionisation is exothermic or endothermic. So if you are putting energy into something, remember that means it's endothermic. So something's only exothermic if energy is given out. So you spoke a wee bit about that at National 5 level. Again, there's a full topic on this which we'll touch on later, so we'll maybe come back to that at a later date. So in terms of the trends that you need to know, so similar to the covalent radius, you need to know the trend going from left to right along the period and down the group, right? So going from left to right, so starting from lithium all the way over to neon, you can obviously see, so these values are straight from the data book, just to make it a wee bit easier for us to see. So going from left to right, we obviously start at quite a low number for lithium, and as we go along, it obviously increases by quite a lot. And then going down your group, it actually decreases. Okay, so what we need to be able to do is explain why that is. So let's have a look. So this is another kind of crazy looking graph, but we'll kind of break it down so that we can see what's going on. So this is actual data, so that we can actually see where these trends are coming from, similar to the last video as well. So in each period, what we've got is a gradual increase going from left to right. Okay, so we need to actually be able to explain that. So imagine we were going from lithium again to neon, you can see obviously the general increase. And the same for sodium to argon as well. So the reason for that, you actually already know. And you've written this already whenever we looked at covalent radius. So this is what I was talking about at the start of this topic. It's the same answers for all of these trends. You just need to know when to use them. So the reason for that is because, well, as you already know, as we're going from left to right, the atomic number's increasing, which means that there's more protons. So that means that you're going to have a greater nuclear charge, you're going to have greater pull on those electrons. So in other words, imagine we had lithium again, so these are the same examples we used last time, and neon, right? So obviously we've got 3 protons in total for lithium, and then 10 for neon. What's actually going to happen is that those 10 protons are obviously, they've got a greater positive charge than the 3 protons, so those electrons are going to be more tightly held towards the nucleus than they would have been in lithium, right? So with that in mind, what actually happens is that if you had to remove one of these outer electrons, you're going to need a massive amount of energy to actually be able to do that because of the really strong hold that's in this nucleus. Whereas if we looked at lithium, it would be quite easy just to take this outer electron away. There's only 3 protons in there, so it's not going to be a massive hassle to get rid of that electron. Okay, so less energy at the left, more energy required at the right. So, moving on. So looking at going down a group then. So there is helium, neon, argon. So again, you can see a kind of slight decrease as we're going. Lithium, sodium, potassium again. Let's have a look, we'll see why. So the same thing, if you're going down a group, remember you're always increasing the number of electron shells. So as you increase the number of electron shells, remember that actually means that the outer electrons are less tightly held to the nucleus. Okay, so remember that shielding effect term, which is where your inner shells actually shield those outer electrons from the pull of the nucleus. Okay, so what that means is that you're going to need less energy to remove electrons from larger atoms. Okay, so for example, if we had, I don't really have much space here, but if we had sodium, which is 281, and then if we go down one, so down that group to potassium, which is 2881, so obviously potassium's got more electron shells, so this wee outer electron here is less tightly held to the nucleus compared to this outer electron here, right? So much less energy would be required to take this away because it's further out from the nucleus compared to this one, okay? So I'd maybe take a wee second to take a couple of notes on that, and we'll take it a wee bit further, because what you also need to be able to do is compare different ionisation energies for different elements. And it could be your first ionisation energy compared to your second one, and then you could do that within different elements as well. So if you want to pause just now, and then we'll do the next bit. Okay, so the next bit, what we're going to look at is comparing first and second ionisation energies. So remember, the first ionisation energy is removing your outer electrons, and then the second one is doing that again, right? So looking at this graph again, you can see obviously this is your first ionisation line down here, and then your second one here. So basically for every single element there is, the second ionisation energy is always greater than the first one. So again, you need to be able to explain why that is. So let's have a wee look. So that's your first one, so just a wee reminder of your equation, and then our second one, which is turning into a 2 plus sign. So basically the reason for that is because whenever you've got your second ionisation energy, so you've lost your first electron, the second one, a lot more energy is required, because what's actually happening now is that you've got a positively charged ion, so you've got quite a big nuclear charge on there compared to the number of electrons that you've got. So that means that there's going to be a greater attraction for the electrons that are left in there. So we're going to need to put a wee bit more energy in to get rid of that second one. Okay, so if you want to take a wee note of that, you can do as well. So as you kind of keep increasing it, so that is just again showing you how to do your wee equations in there. So going from your 2 plus, and then if you ionise that again, that'll be your 3 plus ion that you're making, and then your fourth one to make your 4 plus ion. So as we're kind of keeping on doing it, we need a massive amount of energy, more energy than kind of each time, right? So the reason for that again is because either you've got more protons and electrons, or sometimes we actually end up with a stable shell. So back at National 5, you would have looked at the fact that atoms like to have like 8 electrons in their shell and things like that. So that's what we call a stable shell. So if you kind of try and break into that, you're going to need a massive amount of energy for that again. So we'll have a wee look at that in a second. So this is the last bit that we're going to look at for just now, and we'll try questions later on this, because I don't really want to go into this in too much detail just now, just so you can get your head around it. So the question is, and again this is quite a common exam question, so explain why the second ionisation energy of potassium is much greater than the second ionisation energy of magnesium. So if you're ever asked a question like that, just take it a wee bit at a time. So just writing out your wee equation. So you've got potassium in the gaseous state going to your K plus ion, so you've lost your first electron in there. Just write out the electron arrangement just so that you can see exactly what's actually going on. So 2881, if you're losing an electron, you're obviously going to 288. And then if you're looking at the second ionisation energy, you're going from your K plus to your K2 plus, right? Because you've lost that other electron. And again, just write out electron arrangements so you can see what's happening. So the kind of end result will be 287. So that's fine. So if we look at magnesium, before we even start to answer the question, do the same thing again. So magnesium in the gaseous state is going to Mg plus. So your initial electron arrangement's 282, going to 281. And then if we do the same thing again, so we're going from Mg plus, which is then losing a second electron, to go to Mg2 plus. Okay, so you're losing this outer electron here. So now that we've done that, we can hopefully start to answer this question. So why is the second ionisation energy greater than the second energy of magnesium? So we don't really know what the values are. It's fine just now. If you really wanted, you could look at the data book, but we'll just assume that that question's correct. So let's have a look. What we've got is the second ionisation energy of potassium requires a massive amount of energy. So similar to what I've just said previously. So what we've got here is this stable shell with 8 electrons in it. So ideally that ion would want to stay that way, right? Because that's quite happy just with 8 electrons in its outer shell. And you already know that from National 5. So what we've actually tried to do is turn that into 287, which isn't actually ever possible because it is such a high amount of energy that would be needed for that. Whereas if we look at magnesium, we've got 282 going to 281, which again, ideally, that would actually want to have a full outer shell. So that is quite happy just to get rid of that wee outer electron to become 28, because again, that is stable. Right, so that's actually quite happy just to be 28 and get rid of that extra electron. So not a massive amount of energy is actually needed to take that one electron away compared to breaking into this full shell. Okay, so anytime you're asked a question like that, that's the way I would approach it. I would always just write out the electron arrangements, and then it allows you to visualise what's going on rather than trying to work it out in your head, if you know what I mean. So what I think we'll do, again, you can take this down as an example, and I think we'll try some questions on this. It is quite a lot to take in because it is a relatively new thing that we're looking at. So we'll stop there just now and we'll try some stuff over the next couple of days. Okay, so spend a bit of time, take some notes down, and I'll pop a wee link as well to the BBC Bite Size page on this because the notes are quite concise and they're quite good if you want to use them alongside these ones as well. Okay, so I'll speak to you soon about this and we'll continue later.